Today, we're going to continue looking at integration by substitution. Our goal is to understand how integration by substitution works. And so we're going to look at some examples where integration by substitution works. And then we're going to look at some examples where integration by substitution is not going to work. It's important to understand when our technique is not working or when it's not so that we can understand when it's not going to work. The idea is to bypass the process entirely, look at the integral, identify it as a substitution integral, and be able to write down what the integral is. Your goal is to do less math. This is the goal of every math class. The goal of every math class is to avoid all the technique that you spend so much time on. The only way to avoid all the technique is to become so proficient in the technique that you don't have to do it anymore. That's the important thing. The goal is to get to the point where you're just writing down the answers. That's when you know you understand what's going on. If you, when you still have to write down all this stuff in between, that means you have more practice to do. So the substitution technique relies on two things. First of all, we have to identify something that we can call an inside function. We don't just get to make this choice willy-nilly. When we make this choice, let's say W equals G of X, we have to remember that this is the substitution that we want to make, but this substitution will only work in certain situations. The next thing we need to do is figure out what dW is. That's what makes the substitution go. So whenever you try to make a substitution, you also have to think, what's my dW going to be? You look at the expression for dW, and if you have that in your integral, that means substitution is the method for you. Let's look at one of the examples that we had a couple of days ago that I said was substitution. Classic substitution problem. The goal is to look at this problem and immediately identify the integral of 1/2 natural log of x squared plus 1 plus c. That's what we're aiming for. In a couple of weeks, you'll just look at this one and write down what the answer is supposed to be, or look at something similar, not just memorize this one particular integral. So we have to find something to be the inside function, something to be the W, and then we have to have a dW to make that go. Down here in the denominator, I have x squared. Up in the numerator, I have an x. Since x is the derivative of x squared, this suggests that x squared plus 1 is my inside function. If W is my x squared plus 1 is my inside function, we're already thinking ahead to what we're going to be integrating. So we're reading this as our f of W, or our f prime of W, is going to be 1 over W. I'm thinking if my inside function is x squared plus 1, what's it inside? It's inside the 1 over x function. That's where the natural log is going to show up. Then we have to look at that x up in the numerator and say that is what's supposed to be my dW. If W is x squared plus 1, then dW is 2x times dx. Just take the derivative of what you want the inside to be. W is x squared plus 1. That means dW is going to be 2x dx. We look back at our integral and we don't see a 2 times x dx. but we do see an x times dx. That is, the dw is being multiplied by 2. We can be off by a constant factor. We've got a constant multiple of this 2x dx. We don't have 2x dx, we've got x dx. So our original integral does not have a 2x dx, but it does have an x dx. So we have half of a dw. That is to say, our dw can be off by a constant factor. We just need a constant multiple of that dw to show up in our original integral so that we can continue our substitution. That tells us that this substitution is going to work. I can let w equal x squared plus 1, that dw is 2x dx. So I'm going to replace my x dx with just half of a dw. The function we're actually going to be integrating is a 1 over w. And this x dx, all that is a 1/2 dw. So the x dx the x dx gets substituted for a 1/2 dw, or the other way around. Half dw gets substituted for the x dx. Now that we've got our simpler integral, we're in this integral of f prime of w to w. Now we can integrate to our antiderivative in w. Then we just replace w and get our antiderivative in x. The goal is to know the process so that we don't have to do the process. Any questions? If you think back to derivatives, we know that the derivative of a constant times a function is that constant times the derivative of the function. The constant factors just get carried along. So in the inverse process, the same is true. We just carry along constant factors. Differentiation and integration are linear operators. How's everybody okay? Everybody looks stunned. If you're mildly confused by how the process is supposed to go, congratulations, that's perfectly normal. You're supposed to be confused. We've been at this for like a day. You saw this yesterday. So if you're like, oh, I'm not sure about this, you've seen like 3 examples. If you expect to be like super proficient after 1 day and 3 examples, then you just got the wrong idea about how math works. Question? Once I replace w with x squared plus 1, I look at the x squared plus 1 and I realize that that's always positive. So we can drop the absolute value. Technically, we knew that going into the problem. We knew that the w was always positive, but we want to be careful about how we write things. We are doing math, and math is a very precise thing. It's important that we see substitution not work. The primary reason we wouldn't want to do substitution on this integral, 1 over x squared plus 1, is that we already know what this integral is. We know that this is arctangent of x plus c. That's why we're not going to do substitution on it. But we need to see substitution not work. It's like when you're learning math, you're supposed to get stuff wrong. If you never get anything wrong in math class, then I don't know, you're in the wrong class. You should be in the next one. We might look at this and think the same thing that we had before. W is x squared plus 1. And we immediately run into a problem. If we want w to be x squared plus 1, then I need a multiple of 2x dx to be the dw. Always ask not just what your w is, but what's your dw going to be. If I want w equal x squared plus 1, then I need dw to be a x dx. The 2 doesn't matter. I can just divide by the 2 or multiply by whatever constant we want. I need that x dx. But I look at my integral and we do not have a factor of x to be the dw. So here, we do not have a factor of x to be the dw. This substitution is not going to work. Note that I didn't say substitution isn't going to work. I said this substitution is not going to work. In this case, like I said before, it's okay that substitution doesn't work here because we already know this antiderivative. Is there an E in fortunately? Fortunately. Me neither. I don't trust y'all. Fortunately, we already know this antiderivative. But this is definitely not substitution. So this one works because we did not have that factor of x to be the dw. Fortunately, we already know this, how this one works as well. The degree of the numerator is greater than or equal to the degree of the denominator. Therefore, we should do long division before we begin any kind of integration process. But let's see if our new technique of substitution can work on this. The substitution that we might want to make is similar to the previous ones. Before doing this problem, we had to do the other couple of problems to program you with the idea that x squared plus 1 is our w, our attempted at w. But just led with this one, it might not be a good choice. But if you get set up to make w equal x squared plus 1, then it makes more sense. So I'm like, well, let's try to make w equal x squared plus 1. It's like that thing where you get your friends to pronounce TWO as 12. You're like, oh, how do you pronounce TWA? And you're like, oh, twa. And then twee, and then twoo. And then you say, how do you pronounce TWO? And they're like, oh, 12. You program them to pronounce it as 12, even though you turn around and say, oh no, that's 2. So like if I just led with this, it wouldn't have worked. But I programmed you to be like, oh, w should be x squared plus 1 because it's in the denominator. And I've created a whole new problem by doing that, but we'll deal with that as we go. We can't just decide on what we want the substitution to be. We have to say, what will make the substitution work? What's going to be my dw? And as in the previous two examples, to make this substitution go, I need a factor of x to be the dw. Now, unlike the previous example, we do have a factor of x. Also, unlike the previous example, we got too many factors of x. I've got an x squared in my numerator. If one of them is going to be my dw, what's the other one going to be? That's a problem. So in this case, we have too many factors of x. The problem here is that the numerator is an x squared, and I only need one factor of x to be the dw's. I don't have anything to do with that other factor of x. That messes everything up. So up here, I've got two factors of x. It's x times x. I can grab one of these factors to be, along with the dx, to be the 1/2 dw. So this part, this second one, this one can be 1/2 dw. Well, what are we going to do with that other x? The x squared plus 1, that can be the w. X dx can be 1/2 dw, but I've got that other factor of x up in the numerator we got nothing to do with. We can't just leave it there. We can do the standard Calc 2 student thing and just erase it. And then when I call you on it, pretend like, oh, I didn't see that one. Michael, no, you try to pull one over on me. You try to pull a fast one. And then other students will write down the answer that we got from yesterday as if they didn't just look it up on Wolfram Alpha. By the way, it's always super obvious when you look shit up on Wolfram Alpha. Wolfram Alpha will write things in very strange syntax sometimes, and you'll just copy it. That'd be like the modern version. That's the previous version of just having ChatGPT write your entire essay and not editing it. Just taking whatever was spit out by the AI and trying to turn that in. You know what I mean? I know you're all thinking, oh, we would never do that because I hadn't thought of that before. But seriously, don't just like copy it and paste it and try to turn it in as is. As good as AI is at writing stuff, it still isn't human. And eventually you'll come across a sentence, you're like, oh, wait, what? So. It's very obvious if you try to do this class all on Wolfram Alpha. So the problem here was this substitution wouldn't work because even though I have one x d and x dx, the other x I don't have an answer for. We don't have anything we can fix that with. Any questions? How's everybody okay? I have a stranger example. Remember, the point of the exercise is not just finding the antiderivative. Because if our job is just to find the antiderivative, we'll just make sure that we have a tab open to wolframalpha.com or the Wolfram Alpha app on our phone, and we can take care of that. The point is understanding the process. The point is understanding this particular version of change your variables, because this is an important process that we have to deal with. At this point, you're like, oh, dude, this is starting to look familiar. Do you have any other examples? I'm like, oh, not today. I mean, if you didn't see that coming, then you just aren't paying attention. So you're like, oh, wait, what? No, you're right. I was not paying. It's 8 o'clock in the morning class, and I'm here. Isn't that enough? Once again, we probably wouldn't initially think to do substitution on this. We might look at this rational function and say, the degree of the numerator is greater than that of the denominator. What we should be doing is dividing. Because if this is an improper fraction, let's write it in mixed number form. But let's pretend that we didn't do that. Now, if you're thinking, you're just going to do that on the next page, aren't you? You're just going to divide. You're going to make us sit through that, aren't you? You're like, oh, yes, I can tell you've been in my class before. Well, let's see if substitution will work on this problem. You've been programmed to believe that x squared is a good substitute. Oh, actually, how many people are looking at the x cubed and the x squared and say x squared is the derivative of x cubed? Maybe x cubed should be the w. Some of you are like, oh, well, I don't like the tone of your voice, so now I'm not thinking that. The question is, do I have a factor of x squared to be the derivative of x cubed? More importantly, the question is, why do we not have a factor of x squared be the derivative of x cubed? Why can we not do this? I always forget that this one has two ways to go. Why is this not the substitution? Don't we have an x squared? The problem here is that we don't have x squared as a factor. First of all, the x squared has a +1 attached to it. Second of all, that's not an x squared, it's in the denominator. It's not an x squared times dx, it's a dx over x squared plus 1. So we don't have a factor. Not only does that x squared have a +1 attached to it, it's in the denominator. We have a factor of 1 over x squared plus 1 times dx. The factor where the x that has the x squared is 1 over x squared plus 1 dx. I can't just break off an x squared. Constant multiples, that's the only difference that we get to have. No adding stuff, no flipping stuff over. Multiply by a constant, that's it. So this is not our substitution. This substitution will not work. Any question? So we have to try again. Will the x squared plus 1 substitution work? That was our question. If I want w to be x squared plus 1, then I need dw of 2x dx. I need a factor of x, and I have a factor of x. I've got 3 of them. I've got 2 extra ones. One of those factors of x is going to be my dw. I just have to figure out what to do with the other 2 factors of x. Anybody see what I can do with those other 2 factors of x? The substitution that I want to make is w is x squared plus 1. That's why we're going to be able to do this substitution. One of the x's from the x cubed will be the dw. The other 2, I can just solve and write in terms of w. So down here, the x squared plus 1, this is going to be my w. That was the original idea, the concept for this whole problem. This x dx, all that is going to be a 1/2 dw as normal. That's like everything's working out so far. That other x squared, I can replace with w because w is x squared plus 1. There's no trick to it. It's just a simple trick. I can replace x squared with w minus 1. So this substitution works. I end up with an integral. I'm going to pull my 1/2 factor out in front because I always do. This x squared is going to be replaced with w minus 1. We're dividing by a w. That's actually not the function anymore. It's not a 1/x function anymore. We'll do that. So in this situation, that substitution, x squared plus 1, worked. Specifically because I had 3 factors of x in the numerator. One that could be the dw, and the other 2 that I could easily turn into an expression in w. If that had been a w to the 3rd power, this would not have worked. Or an x to the 3rd power, because we started with x to the 4th, this substitution would not have worked. Now, in this scenario, we've got w minus 1 over w. The advantage we have here is there's only one term in the denominator, so we can use the distributive property. So I can rewrite this as 1/2 the integral of w over w minus 1 over w dw. Now, if you drop this into Wolfram Alpha, this is probably not the same thing, that you're going to get, but we've gone through all the steps. How's everybody okay? That last part went a little fast, because it became one of our base integrals. With the right terms as powers of w, that we did. We read the 1 as a 1 to the 0 power, then we add 1 to the exponents and divide by the new exponent. So when we see that 1, we're thinking w to the 0 power. And so we add 1 to the exponents and divide by the new exponents. Good question. I 100% just glossed over that. So you might have looked at this problem initially, and since I talked about rational functions previously, you said this is an improper fraction style. And the way to deal with improper fractions is to use long division. So let's take 1,000 divided by 101. In this case, how many times can we subtract x squared from x cubed? We can do that x times, because I have to multiply x squared times x to get x cubed and allow us to subtract. But I have to subtract this whole thing. X plus 1 is plus x. And so we subtract. X cubed minus x cubed is nothing. 0x squared minus 0x squared is 0x squared. X minus a 0x minus an x is a minus 1x. And at this point, we can't subtract full powers of x. I'd have to multiply by 1 over x. I don't want to get into that. At least not until second. So if we apply long division to the problem, then we would rewrite our integral of x cubed over x squared plus 1 as x minus x over x squared plus 1 dx. And now we can just integrate a term at a time. The integral of x is a 1/2 x squared. And the integral of x over x squared plus 1 is our first example of the day. So that's going to be a 1/2 natural log . So good news, there are many ways that you could have approached that. 2 ways that you could approach this problem. Bad news, there are 2 ways that you can approach this problem. We all think we like choice until we have to make a choice. You know what I mean? Classic D&D problem. Players be like, this campaign is just on rails. It's like you don't have any choices. Then you give players a choice. They go, well, I don't know what to do. Well, I can just tell you, you know, you technically are easy. What it comes down to is too many choices. What the players would be happy with is like, oh, you want to do A, B, or C. You don't want to ask them that directly. You're like, well, A, B, or C. Like, oh, we'll do this. You know what I mean? Like, imagine if you're going to buy a car and you want a compact SUV. Well, shit, there's too many to choose from. RAV4, CRV, Mazda CX-5. Hyundai has one, Kia has one. Trick question, those are kind of the same car. But there's lots to choose from, right? So I go, oh, which one should I get? Which one is best? And you look at the MPG, it's like, oh, this one's 24 MPG, which is better than 23 MPG. At which point I'm like, oh, really? By how much? How much money does that translate to? It's more though, you know what I mean? But it's not a useful measurement. Problem is, there's too many choices. What if there were only two cars that you could choose from? You can either buy the Toyota RAV4 or a Ford F-150. Those are your only two choices. Ford F-150 only comes long bed, two-door version. You either get a two-door F-150 with a long bed or a Toyota RAV4. Those are the only two cars you could possibly choose from. Now the choice is simple. Well, I have humans that I need to carry around, and it's more than 2 or 3, so I'm going to have to get the RAV4. I know car enthusiasts in the room are like, oh, this is a horrible thing that you proposed, Leach. What are you doing? So I'll make 3. Your third choice is a rear drive, inexpensive sports car. The one that sports enthusiasts always want until they're asked to buy it, in which case they don't buy it. Make a cheap 2-door rear drive sports car. So it's like, oh, here you go. I'm not buying it. Not in the power. You're gonna stick a turbo on it anyway. You're gonna order some cheap ass turbo off of eBay and blow the thing up and then complain that the car blew up. Meanwhile, you put a bomb in the car, so what did you expect? Do you know what I mean? What I'm saying, car enthusiasts are their own worst enemy. If you're a car enthusiast, I'm making fun of us. It's like Star Wars. Star Wars sucks because of the fans. Star Wars would be a much better product if they didn't have like all the fans. And George Lucas. Or if someone would just stand up to George Lucas and say, no, George, we need to do something else, like he had in the first 2 movies. Anyway, the important question is, you're going to notice that, wait a second, this is not exactly what we wrote in the previous one. That looks different. What's different? You might be like, oh, yo. So to explain that would make everything super clear, and calculus, no problem. You really understand everything what's going on with calculus. All I got to do is tell you where that 1/2 went. First of all, if you're looking at where that +1 go, that's not a +1, it's a 1/2, right? You got to multiply stuff out. You're already forgetting your distributive property. I thought you guys said you've been through algebra. Now, come on. So you might be looking at this +1 and say, where'd this 1/2 go? Why do we have that +1/2 in our answer down here? Now, all I got to do is answer this question. Once I answer this question, all the rest of calculus and integration in particular will be super simple and you'll understand it instantly. But I have to tell you right now, if I don't tell you right now, then we're just going to have to go through calculus the normal rate. You're going to have to struggle, you have to do work, and you're going to have to practice. So let me explain where that 1/2 went so that you'll understand calculus forever instantly. Now, the reason we don't have the 1/2 is, oh, look at the time. I guess that's it for this week. I'll see you all on Monday. Everybody have a good weekend, and thanks for playing.